Don't know the answer? Ask the Naked Scientists.
Hello, welcome to this week's edition of Ask the Naked Scientists with Chris Smith and with me, Matt Jamison. Let's get straight to Tony. Good evening, Tony.
Good evening, sir.
Thanks for holding for us. You're
Not
through to Dr. Chris. What's your question?
Right. We've heard about this amazing great sun that they've discovered. Now, it is a relatively new sun, I believe. I'm not wonderfully up on it. But when I say it's new, I mean, where on earth does it come from? I mean, especially a thing like this, which is enormous. Is it part of something that's already there, I suppose?
Hello, Tony. Yes, you're referring, I think, to an announcement by Paul Crowther, who's from the University of Sheffield. He and his team have been looking at various clusters of bright patches in the night sky, and this is where there are masses of new stars being formed, and they spotted one which is excitingly called R136A1, and this baby is something in the region of 250 times the size of our own sun. So this is probably the largest star that's ever been spotted. How long it will remain so will be, well, I don't know. It depends until someone finds one which is larger, if they can exist. But why this is interesting is that it's so massive that it currently means that our understanding of how stars form and how they live and die needs a little bit of adjustment, because this star shouldn't exist because it's just too big. Where do they come from? Well, what we think is happening, and the reason that people like Paul Crowther are studying the night sky, is to look at large fields of view to see many, many stars in order to see them at different phases of their life, so that we can begin to understand how stars like our sun are born in the first place, how they evolve and change, and what their ultimate outcome will be. And what the researchers were doing was just looking at various patches of the sky, and they spotted this star, which was extremely bright. And by making various clever measurements, they actually discovered it does weigh something in the region of 250 times the mass of our own sun. And it's extremely hot. The surface of this star is about 50,000 degrees C. And to give you a comparison, our own sun has a surface temperature of something like 5,000 degrees C or 6,000 degrees C. So it's a good 10 times hotter than the surface of our own sun. And this is the important point, because the bigger a star gets, the brighter it gets, because the more fiercely it burns. And that's because the mass of the star increases the gravitational pressure, the amount it's squeezing in on itself, and that in turn accelerates the fusion process, the merging of smaller elements to make bigger ones, which is what produces energy and which is what makes the star give out heat and light. So the bigger it is, the more that happens, and therefore the brighter it gets. And stars which are this big don't live very long. So stars like our own sun, which are quite medium size or small, they will have a lifetime of maybe 10 billion years, during which they turn all of the hydrogen, which is what they are largely made up of when they first form, into bigger elements like helium, and ultimately in some big stars things like iron. So they make elements in the process of evolving. But our sun will probably last 10 billion years. This one will be lucky to make a few million, because it's so big that it will basically blow itself to pieces very, very quickly, because it gets so hot and it will eventually just explode in a massive supernova. What makes it form in the first place? Well, good question, and that's what scientists are trying to understand. We know that stars are massive balls of gas and dust, and that hovering in space where a star forms, there must be a big aggregation of gas, largely hydrogen, because the majority of the things that were produced in the Big Bang about 13.5 billion years ago when the universe formed was hydrogen. And so as a consequence of that, most of that hydrogen then collapses together, makes the star as it all collapses in, and then you end up with that beginning to unite, hydrogen atoms joining to hydrogen atoms to make helium, and you've got a fusion process, and off it goes. What actually makes all that gas come together and begin to collapse down in the first place, we're not 100% sure yet. Chris at thenakedscientist.com if anyone wants to drop me a line. Or
Which
you
is
can Twitter at us,
exactly...
of course. You can do at Naked Scientist if you want to send us a tweet.
Tweets? Facebook? Have you got Facebook yet?
Yeah, we've got Faceache. Just look up Naked Scientists on that too. You'll find us there.
No, that's
Used
exactly what Gary Mason did. He said, "Hey Chris, massive fan of the show. I have all the episodes of Naked Everything.
It just goes to show there are some people out there who really do need help.
Yes,
including me. But there we are.
My little girl has a spoon that changes colour if her food is too hot. It's red when it is cold, but when you run it under a hot tap, it changes yellow. How does this work? I've also had cars when I was a kid that did the same thing. It changed colour by the heat from your hands. That's from Gary Mason. Over to you with that one.
My children have got some ducks that you put in the bath that do the same thing. They're obviously plastic, they're not living ducks. You put them in the warm water and they change colour. And this is something called a thermochromic effect. And there's a number of ways of doing this, actually. One way is to use liquid crystal, the same stuff that you see in screens, computer screens and calculators and things. And what you've got going on in liquid crystal is certain molecules which have a very planar shape. Now, what that means is if you looked at the molecule from the side, it would be long and flat, for example. It wouldn't be a ball of wool, it would be a flat, rigid shape. And when you make these things warm, what can happen is that the molecules want to line up together in a certain way because, say, one end of the molecule might have one charge and one another charge. And if you warm them up, it makes it easy for the molecules to flow past each other and line up in this particular configuration. And when they do so, what that does is mean they interact with light at a slightly different way. So they'll block certain wavelengths of light, but not others. And as a result, you see a change in colour from the surface that gets reflected back to you, so the surface changes colour. That's one way of doing it. Another is to use big molecules, and these tend to go by the name of leuco dyes. And the way these work is that you change the way in which they share electrons amongst themselves. So if you look at something that's got a colour, and flowers are a really good example of this. There was a guy called Willstatter, who was a German scientist in about the 1920s, I think. He got the Nobel Prize for describing this. He was interested in all the different colours of flowers that you see. And you might think that lots of different flowers achieve their different colours by making different chemicals in their petals, which give the petals their particular colours. In fact, they make very few chemicals, and chiefly they make one, anthocyanin, and they make their colours by just chemically tweaking that particular molecule, by changing how acid or how alkaline the environment of the cells are in which that molecule is found. And when you make the molecule a bit more acid or a bit more alkaline, what you do is to affect the way in which electrons get shared between the atoms in the molecule. And when you do that, it means that when light passes across the molecule, some wavelengths of light get absorbed and others don't. And when you change the shape of the molecule by adjusting the way in which the electrons are being shared, then different wavelengths of light get absorbed and others don't. Because remember that white light, what we see as white, is a mixture of different colours all blended together, which we see as white, but which Isaac Newton, Cambridge scientist, showed you can split apart with a prism and see all the different colours. And so those individual different colours are interacting with these molecules in slightly different ways, and temperature can affect the way in which those molecules share their electrons, and that's what drives the effect.
Gary, we hope that's answered your question. Thank you for emailing chris@thenakedscientist.com. Another question from the website, Dr. Chris, comes in from Andrew McCluskey saying, I was wondering how pain relief drugs target pain and why we don't just go numb in random parts of the body.
It's a very good question. The way in which they work is that the drugs don't actually target the painful bit of the body. They go everywhere. And what they're affecting is the process that takes place wherever something gets injured to make that area painful. So if you take paracetamol or aspirin as an example, if I take a paracetamol or an aspirin and then I injure my finger, what would normally happen if I injured my finger, say I cut it or something, is that I would do a number of things. One, I would aggravate sensory pain-sensing nerve fibres in the skin, and they would immediately start to say, ow, this area hurts a bit, it's been injured. They would also trigger the release of inflammatory factors from various cells in the injury site, which would then start to produce a whole load of other inflammatory factors, which would then attract the immune system to come in, and this would produce even more inflammatory factors, which in turn makes the sensory nerve fibres even more sensitive, and therefore you experience even more pain and the area becomes inflamed. Now, the things that do this job are a family of molecules called prostaglandins. Prostaglandins get made by an enzyme called cyclooxygenase. So what happens is that when an area gets injured, some cyclooxygenase enzymes get turned on, and they break down something called arachidonic acid into various other substituents, which eventually becomes cyclooxygenase substrates, which become prostaglandins. And they wind up sensory nerve fibres, they open up blood vessels so that more blood flows to the area, and that's why it goes red. They also make blood vessel walls leaky, which means that things come out of the blood vessels like cells, and that's why the area gets swollen. And they also activate the sensory nerve fibres, and so that's why they get painful. Now, what aspirin and paracetamol do is they lock onto that cyclooxygenase enzyme and block it up irreversibly. So it can never make any of these prostaglandins. So the area that's been injured then can't get inflamed as much as it would do normally. So everywhere in the body this is happening, but it's normally the area where you've had the injury that the wind-up would happen. And so that's why you get relief that appears to be focal, but in fact it's a whole-body effect. So that's the chief way in which these things work. Of course, there are other ways to numb pain. Local anaesthetics, which you might have if you're going to have a minor operation or something, they work by actually binding to nerve fibres, going inside the nerve cell and blocking up little pores on the surface of the nerve cell, which is going to allow the nerve to get active. So if you block those pores up, the nerve cell can't signal the pain. And then there are other things like morphine and opiates, and they work in various ways, one of which is to go into the spinal cord, and they suppress the activity of nerve cells that transmit the pain signals up into the brain. And so you can turn off the flow of pain going up the spinal cord with things like morphine. So there's a number of ways it can work. One, the simplest way is to block the inflammation at the site of injury, like aspirin and paracetamol. Then there's actually inhibiting nerve fibres with local anaesthetics, or using whole-body things like morphine, which block the flow by inhibiting the cells that transmit the information up into the brain in the first place.
And Jenny in Northamptonshire has been very patient, wanted to know about the latest discoveries in regards to protons and how they affect quantum electrodynamics. Over to you, Dr. Chris.
Yeah, this was a story which came out, I think it was about a month ago, and the big headline was, "The proton just got smaller." Protons are pretty small. In fact, the sort of previously accepted value for the size of a proton was about 1 femtometre across. A femtometre is 10 to the minus 15 metres. So in other words, you would have to put 15 zeros after your decimal point to get to your number. And that would be a 1. So they're very, very tiny. And they just got a bit smaller, it turns out, because what scientists were interested in doing was working out whether or not the value we're using for the proton, of course, being the positive charge in the nucleus, which is the site at the centre of an atom where all the positive charge and the neutrons associate together. And this is important because understanding the atomic structure means that if we get it wrong, then a lot of the predictions we're making about the way that science should be being done and understanding how, when we do experiments, what the outcomes ought to be, in other words, what we should be looking for, those sorts of things rely on accurate measurements. Now, the proton was first measured, I think, about 50 years ago by researchers in America, and what they were doing was firing various charged particles at protons and then measuring how much the protons deflected those charged particles, because then you can work out what the mass to charge ratio is of the thing you're firing at it, and therefore how much it should bend based on the size and so on. So you can work out the basic size of the proton, and that's how they arrived at this number. But then a group of researchers thought that they would do some basic experiments around this, and this is a guy called Randolph Pohl, who's a researcher in Germany. So they were repeating some of these sizing experiments, and they were doing some quite clever stuff where what you do is to measure for if the proton size is right, you should be able to produce energy at various levels coming off an atom. And when they did these experiments, they couldn't detect this energy at the frequency they were expecting to find it, so they thought something was wrong. So they went and had a closer look. Now, what they did was to take hydrogen, which is the simplest atom. It's got 1 proton in its nucleus and 1 electron whizzing round the outside, and they replaced the electron with another charged particle called a muon, which is much heavier than an electron, but also negatively charged. And you can make something called muonic hydrogen, and doesn't last very long, but long enough for them to do an experiment where they then zapped these things with a very powerful laser to put some energy into the atom. And what this does is make the muon get a bit more excited and jump up to a certain energy level, and then give out that energy again when it goes back to its original energy level. And if they'd got the size of the proton right, then what they should have done is to measure light coming off from the atom at a certain wavelength. And when they did that, they couldn't find it. In fact, when they went hunting, they found the light was coming off at a totally different frequency, and this could only be explained if the proton was actually 4% smaller than we thought it was on the basis of the early experiments that were done 50 to 100 years ago. So this means that we have to actually think quite carefully about the structure of atoms. We have to revise our models and obviously confirm that this is correct. The proton is 4% smaller than we thought, but it also means the predictions we're making about various experiments and things are going to need a little bit of tweaking too, because for some things that are not giving positive results, we may have to think again and revise our estimates and how we look for the answers, because we may be looking in the wrong place because we had the sizes slightly out.
Now, you've got a tweet you're going to read out now, and then we've got Paul from Gorston on the phone.
Very lucky we've got two. One very quickie. David Worley, 94, has tweeted to @NakedScientists, what is a photon? Well, a photon is a particle of light. Now, we talk about light as behaving both as a particle and a wave. Light is an electromagnetic wave. What that means is that you have a disturbance, which is a bit of electrical current flows, and because you get a flowing electrical current, you make a change in a magnetic field, because currents make magnetic fields. So if you then make a changing magnetic field, you make a changing electrical field, and that in turn makes another changing magnetic field, and so on. And you get this wiggly wave, and that is how light propagates. And light and radio waves and microwaves and X-rays and gamma rays, they're all electromagnetic waves. Now, everyone thought that light was just a wave until Albert Einstein, in about 1905, published this seminal paper, which was the one that won him the Nobel Prize, actually. It was nothing to do with relativity. He got the Nobel Prize for describing something called the photoelectric effect. Because people, although they had this concept of light as being light waves, because Isaac Newton had shown that there must be something like that going on, what we couldn't explain was that why, if you shone certain wavelengths or colours of light on a surface, some of them could produce electricity, and some of them couldn't, and some wavelengths produced more electricity than others. And this suggested that different wavelengths of light must be packing a harder punch than others. And it was Albert Einstein that then realised that light actually can be considered to be arriving in small packets. He called them quanta, and those small packets have more or less energy associated with them relative to the wavelength of the light. So blue light, for example, has far more energy in it than red light, so therefore you will get some electricity produced with blue light, but not with red light. And that's why ultraviolet light is ionising and can damage you, but infrared is just nice to warm you up. So that's what photons are. They're chunks or particles, quanta of light, as Albert Einstein described over 100 years ago now, which is quite amazing. Now, my other little tweet is from Alfie Stepani, who says, why do we, like David Cameron, get grey hairs? Everyone's entitled to. Why does it happen? The reason is that in your hair follicles, which are little collections of stem cells in your skin, which make hair, and hair is a protein, it's keratin, the same stuff your fingernails are made of. Also in those hair follicles are cells called melanocytes, and melanocytes make melanin, the coloured pigment that goes into the skin that can give you a suntan. It also adds melanin to your hair to give hair its colour. And for some reason, and we don't know why, in hair follicles, those melanocytes expire. They get old, they senesce, and they stop working very well. And as a result, they stop adding this dark or darker or coloured pigment, because there are different types of melanin. There's some which is very black, that's eumelanin. There's other forms of melanin which is yellow colour, pheomelanin, and that's why you get different coloured hair. For some reason, they stop adding that coloured melanin to the hair filament, so you just see the native colour of the keratin, and that is a white colour, like your fingernails, where they grow out beyond the growth plate and they look white. So your hair goes to that colour.
It's fascinating stuff. We do have possibly the most patient listener on the phone, Paul from Gorston, who says apparently drinking seawater can have various effects such as swollen joints, etc. If we eat a lot of salt and drink a lot of water, could this have a similar effect? Paul?
Hello there.
I've asked your question and it's put through. Here comes the answer. Stand by.
Hello, Paul.
Hello.
Well, the amount of salt that you take in your diet is actually directly relevant and proportional to your blood pressure, because there was a big study that got done called the InterSalt study, and they showed that people who eat more salt have higher blood pressure than people who don't eat salt, and this accumulates over a lifetime. So lifetime exposure to salt translates into a steady increase in risk of high blood pressure. The reason for that is not really very well understood, but probably relates to the fact that salt draws water with it. So if you have lots of salt in circulation, you have more water in circulation, and this means that your blood vessels are slightly more full or stretched, to put it a sort of slightly simple way, and that puts your blood pressure up. So just eating lots of salt and drinking lots of water isn't a good idea, because it will probably translate into high blood pressure, which carries with it a risk of stroke and heart attacks and things. But in terms of whether there will be other onward effects, there's lots of other things that might be in salt. If you get sea salt, there's lots of iodine in that, iodide, and as a result you won't get a big thyroid, which people in Derbyshire used to historically get before we used to get good movement of food from the coast to the Midlands, or fortification of salt with iodine. People in Derbyshire used to get Derbyshire neck, an enlargement of their thyroid, because they didn't have enough iodine in their diet. There are other things in salt too, lots of trace elements and things, and if you take too much salt from sea salt, for example, there's a risk that you might become overloaded with some of those other trace components too, and they might have consequences. So I think the best thing to do is to stick to what the current guidelines are, which is, I think, less than 6 grams of salt a day, and that is not hard to exceed, believe you me. Have a packet of crisps and straight away you've had half your salt ration for the day.
I've also read about the side effects of swollen parts of the body and swollen joints and so forth, and is it the ancient mariner that you can cause madness as well? So is there any sort of, like, I know there is a safe level, but would any sort of, percentage of it have any sort of effects of those symptoms, basically? And what about table salt? Does that have a similar effect if you sort of drank water? And I don't know what type of salt crisps have it. I presume it's is it sodium chlorate or whatever, table salt?
Sodium chloride, that's right.
Yeah. So what effect would sodium chlorate and water have? As opposed to sort of seawater.
Well, sea water is just water with a whole bunch of salt dissolved in it, and so if you were to eat loads of salt and then drink loads of water, the salt would dissolve in the water you drank, so it would be equivalent to drinking seawater, and all that salt would be absorbed, go into your body, and then you've got to deal with it because the body has to get rid of the excess sodium. So your kidneys would have to filter off the excess sodium. You need some salt in your diet, but not as much as many people in eating a Western diet are eating every day. We're probably exceeding by a long way the amount of salt that we ought to be eating, because it makes food taste good, and we've got used to eating processed food with a very high salt content, and as a result, when we eat stuff that doesn't have all this salt fortification, way beyond what we need actually, it doesn't taste so good. So people go, ugh, and add more salt, and you're back to where you started.
That's it for this week. Thanks for listening. Remember, you can send The Naked Scientists your questions by email. chris@thenakedscientists.com is the address to write to. And if you want to find out more about The Naked Scientists, then drop by our website, nakedscientists.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.